Hey guys, this is Professor Janacek. Want to talk about a power series today. Want to specifically look at the Maclaurin series. Now, quick review of a Taylor series. Taylor series for f of x about x equal to a has the form f of x is equal to the sum as k goes from 0 to infinity of the kth derivative of f evaluated at a divided by k factorial times x minus a raised to the k. That's a Taylor series. Turns out the Maclaurin series is simply a Taylor series centered about x equal to 0. So anywhere where we have an a in the Taylor series, we simply replace it with 0, and that gives us a Maclaurin series. Let's try an example. Let's find the Maclaurin series for the sine of 3x. So in this case, our function f of x is sine of 3x. To begin with, we're going to need to find the kth derivative. See if we can find a pattern for the kth derivative. Then we'll evaluate that at 0. So, the first derivative of sine of 3x is 3 cosine 3x. Yes, we're using the chain rule there. The second derivative is negative 9 sine 3x. The third derivative, we get negative 27 cosine 3x. The fourth derivative gets us back to a positive 81 sine of 3x. The fifth derivative is 243 cosine of 3x, and I think that's enough. That should be plenty for us to figure out what's going on here. Now we need to evaluate these at 0. F of 0, sine of 3 times 0, well 3 times 0 is 0, sine of that we get 0. F prime of 0, if we put a 0 in for x, we end up taking the cosine of 0, multiplying that by 3, we end up with 3. Second derivative of 0, we end up with sine of 0 again, that gives us 0. Third derivative at 0, we end up with negative 27. The fourth derivative at 0, we get 0 again. The fifth derivative at 0, we get 243. And again, we'll stop there. I'm starting to see a pattern. I noticed that we're alternating with 0. I also noticed that the numbers that we do have, we start with a positive 3 to the first power, and we get negative 3 to the third power, and the next one is positive 3 to the fifth power. This might be helpful when coming up with this series later. All right, well, let's jump in and see if we can find this series. Now, our original function, sine of 3x, is what we're looking at, but using our little pattern here, this function is going to be the sum, as k goes from 0 to infinity, of the kth derivative evaluated at 0 over k factorial times x to the k. So that gives us the sum as k goes from 0 to infinity of the kth derivative at 0 over k factorial x to the k. Well, let's write out a few of these terms to see if we can see what's going on here. When k is 0, we have the 0th derivative at 0, which is really just the function, over 0 factorial x to the 0. When k is 1, we have the first derivative over 1 factorial x to the 1. K is 2, it's the second derivative over 2 factorial x squared. K is 3, it's the third derivative over 3 factorial x cubed. When k is 4, it's the fourth derivative over 4 factorial x to the fourth. When k is 5, it's the fifth derivative over 5 factorial x to the 5th. Again, we could continue on, but we'll stop there. Now let's go ahead and fill in some of our values. We know those derivatives. So let's see. We have 0 over 0 factorial x to the 0. And all I'm going to do is replace the derivative values. We'll simplify the rest of it here in the next step. Then we have 3 over 1 factorial x to the 1. Then we have 0 over 2 factorial x squared. Negative 27 over 3 factorial x cubed. 0 over 4 factorial x to the 4th. And 243 over 5 factorial x to the 5th. Now, I'm going to do a couple of things here. I notice anytime I have 0 in the numerator, those terms just become 0, so I can get rid of those. The other thing I want to do is I'm going to go ahead and change these numerators. We already saw that we can write those as powers of 3. So, this simplifies down to 3 to the 1st power over 1 factorial x to the 1st plus, actually, oh, no, it's going to be minus 3 to the 3rd power over 3 factorial x to the 3rd plus, we skip a term, we end up with 3 to the 5th power over 5 factorial x to the 5th. And I think that makes a very nice pattern. We see that the exponent, the number in the denominator being factorialed, and the exponent on the x all have the same value, and I see that those are all odd numbers. So the pattern is odd numbers in those spots. So let's see. That means that our function sine of 3x can be written as the sum as k goes from 0 to infinity. Now, first thing I'm going to write is the alternating sign. I want an alternating sign starting with a positive. That is negative 1 to the kth power. Remember, k is starting at 0. So when k is 0, negative 1 to the k is just 1. When k is 1, negative 1 to the k is negative 1. So that gives me my positive, then negative, then positive. Then we have 3 raised to, now we're looking at odd powers. When k is starting at 0, to get 1, I'll use 2k plus 1. That's going to give me my odd powers, odd numbers when k starts at 0. In the denominator, we have that odd number factorialed. And then here in the back, we have k raised to the 2k plus 1 as well. Now, yes, you could combine these. I'm going to go ahead and keep this separate so I can see what the coefficients look like, but you could definitely combine some things if you wanted to in this case. But there we go. There is the Maclaurin series for sine of 3x. Enjoy!